Hello everybody. In the last class we started with 86 arithmetic instructions, and in today's class we'll see little more about arithmetic instructions. In the last class we discussed about addition, subtraction, increment, decrement and comparison, and today we'll take up multiplication, division and decimal adjust, right? So there are two different commands available or syntax available. Two different sets of instructions are there for multiplication. One is multiplication, which is for unsigned multiplication, and one is IMUL. It means it is signed multiplication. Okay, so integer multiplication. So IMUL stands for that. So if you see why these two different kinds of multiplications are required, because let's take an example. This is 255 decimal. It's an 8-bit into 8-bit. I am getting an 16-bit okay data, which is 65025 okay in the decimal. So this is how it's represented in the binary. So a hardware needs to be implemented which will give these results. Okay, but if it is an signed multiplication, right? So the computer doesn't know whether the data which you write is signed or unsigned, right? The microprocessor doesn't know, right? But it is your algorithm, right? If you are considering this as a signed multiplication, right? In that case, this represents -1 and this represents -1, and you would expect the microprocessor to do -1 and -1 and give you a result of +1, right? So see, it's the same thing here, right? It is 255 into 255 in unsigned multiplication, whereas if I consider this as -1 and -1, because suppose I am writing a program where I have to handle negative numbers also, in that case these represents -1, right? So the answer has to be like this. So the processor has to use a different algorithm or a different hardware to get these two different results, right? So that is the reason in 8086 we have two different syntax or two different instructions for multiplication. This is for unsigned and this is for signed. Okay, so let's take some of the examples and things will be clear. Now suppose let the first we'll see 8 into 8 and multiplication. Obviously when you are doing an 8-bit and to 8-bit multiplication, the result will be an 16-bit, right? It can be a 16-bit, right? It can, so if these are smaller numbers, the result can be 8-bit also, but generally speaking, you have to at least cater for a 16-bit register to hold the result, because 8-bit and 8-bit multiplication can result in an 16-bit data also. Okay, so that's and hence so the first syntax is multiplication source. Now since we are talking about 8-bit into 8-bit, I can write mul and then I can write as source. So this source can be any register, okay, and it can be an 8-bit register. Okay, that is it can be it can be BL or it can be BH, it can be CL, CH, DL, DH and so on and so forth. Okay, so this can be this source can be an 8-bit register. Now you don't have to specify the other register, because by default AL will be taken, okay, as the other number for multiplication, right? So AL will by default will be, so here only one register needs to be specified, the other will be default, and once the multiplication is done, the result will be stored in AL. So obviously the contents of AL also will get modified, and once you get the product, the lower 8 bits will be stored in AL register and the higher 8 bits will be stored in the AH register. Okay, so the 16-bit result is placed in the AX register. Okay, so higher the result product will start from here and from the higher bit to the lower bit. Okay, entire AX register will be used. Obviously initially you have to load the AL register with one of the 8-bit data which needs to be multiplied, and the second 8-bit data, okay, you can give the address, right? Either it could be a register or it could be a memory. Okay, now here 8-bit source, so this source can be like it can be BL or it could be BH, CL, CH and so on and so forth, right? This is not permitted. Direct, immediate multiplication, like we saw in the case of addition and subtraction, so that is not permitted here in the multiplication. And also we can take an information, we can take an 8-bit from the memory also. So obviously since it's an right, it's an 8-bit information we need to take, that a single byte has to be taken from the memory. So once we are specifying the memory location, so memory location is indicated by a 16-bit address which is there in BX, but you need to specify a byte PR. If you don't write byte PR, then it could result in an 16-bit multiplication also. But if you are interested only in a byte multiplication, then you need to specify this byte PTR. Okay, so this is how an multiplication, 8-bit multiplication would be executed, right? Now, similarly, if it is an 16-bit, right, in that case, I just write an mul BX. Suppose I write, okay, I can write in a CX also. So if I write in a BX, or I could write in a word in a PTR and a DX, right? I can write. So all these things are representing in 16-bit data. So by default, the contents of AX will be taken as one of the multipliers, right? And it will multiply. Now you are multiplying 16 into 16, so the answer would be 32. So you will require two 16-bit registers. So the higher bits will be stored in DX, and the lower 16 bits will be stored in AX. So this was AX, so that will get modified, okay, with the lower 16-bit product, and this would remain as this also. Obviously the higher bits data will come into the DX register, right? And in 80386 at all, we know we can do an 32-bit operation also. So you can specify a 32-bit source. In that case, the EAX will be taken, a 32-bit register EAX, and then the result will be stored in EDX and EAX together. So this will be 64-bit data. So let's take some examples so that we understand. Now before that, let's talk about the flags. Okay, and now when we do the multiplication command, right, when we write the multiplication command, actually the flags are set depending on the AL register only. Okay, it doesn't, the flag is not set as per AL and AH together. It is just for the flags are set as per AL, and that is the reason only two flags will be valid, which is carry and overflow, and the other flags, although they get affected, but they should not be taken into consideration because they could be false. Okay, so they are undefined. So only we need to bother about these two flags. Okay, I'll tell you the logic why it has been done like that. For example, I have to do 10 into 25 multiplication. Okay, 10 and both decimal numbers. So I'm moving 10 into AL, and I'm moving 25 into DL, and I'm just writing move DL. Obviously, I don't have to specify AL here, right? And since it is DL, it does an 8-bit multiplication. Now, so the answer will be 250, and the 250 answer will be put into AL register, and an AH register will have 0000, right? AH is actually the resultant answer. Since the flag is dependent only on AL register, okay, the carry flag will be 0, and overflow flag also will be 0, because this answer is 8-bit, right? So this gives me an indication that the AH register has not been utilized. Okay, so when I'm doing so probably say suppose I am doing 1 into 2 into 3 into 4 like that, right? If I do 1 into 2, it is still an 8-bit multiplication. Then I can do the result into 3. okay, again the result will be 8, right? So but I have to know that this result is 8 bit, right? If I don't know that the result is 8 bit, then what will I do in the next, right? And in the next step, I will I will assume this is to be a 16 bit operation, and then I will start multiplying. So that will unnecessarily take a longer execution time as well as longer memory. So if the result is 8 bit, I should know that that result is 8 bit, so that I can again use an 8 bit multiplication. Or if I am going to store it into the memory, I need not store it into a full word. I can store it as a byte also. So it is very, very important for us to know that the result is a byte or a word, right? Now, although normally both the registers and the result will be here, but if this is all 0 0 0 0, then what? Then we should know, right? So how that can be known? Because this flag is set based on the AL register. So if there is nothing going into the AH register, then the carry and 0 flag will be 0, and I will come to know that okay, the result is available only in the AL register, and the product is just an 8-bit information, and accordingly I can make my further decision. Okay, so that helps. Now suppose I do 10 into 260. Obviously 260 cannot be stored in an 2-bit register, in an 8-bit register. So obviously when I do this multiplication, some data will be appearing in AH register also, and accordingly carry and the overflow bits will be set to 1. And then I will take this data both together, okay, for the subsequent operations. Okay, so that is it. Now suppose let's take one more example. Here we have to multiply two numbers, two 8-bit numbers, which are stored at offset 100 and starting from 100. So obviously the next byte will be at 101, and store the result into 200. So first I take this 100 into SI register, and this is the destination register. So I take it into DI, and I move that contents which is available at 100 to AL register. Okay, so that is that. Now I have to get the next byte. Okay, so I can increase BSI. So now SI is pointing towards 101. So I can do multiply byte BR SI. So the whatever was in AL, what is in AL? The data which was available at offset 100, it is multiplying by SI, and what is now SI, since I have increased, it is 101. So that next that data will be multiplied. Now where will be the answer be available after this operation? It will be available in AX, and from AX I can move it to DI. So DI is the where we wanted to store this data in 200. So we had already moved that 200 into DI. So accordingly this result will go into to a memory location indicated by DI. Okay, so this is an example of how a multiplication can be done. Right now in the assigned multiplication, okay, we use IMUL. Okay, so that is the I integer multiplication. Okay, and then we specify the source. Now this source can be an 8-bit or a 16-bit, like in the case previous case. Okay, so now here in this case, under the carry and the overflow flags are set if the upper half of the result is not sign extension of the lower half. Okay, that means it means the same thing, that only my if they are not set, if the carry are set, that means it is are set means if the upper half is not an sign extension of the lower half. Okay, so if you take an example, if I do 1 into 66, okay, minus 1 into 66, okay, so this is the result which we get, right? Now if you see, this is the sign extension of this. Okay, so in a signed number, only this much represents 66, and this is just the sign extension. Okay, and since it's an sign extension, carry will not be generated. Okay, carry on will the carry, and this is 0. Okay, so in case Now I do -1 and minus 66. If I multiply, the answer is 66. In this case also, if you see here, these are all 66. The answer is 66. So this is also 66. This is just a sign extension. Okay. Now if you see here, 25 into minus 10, it is minus 255, right? So minus 255 cannot be represented in an 8-bit. Okay, in an 8-bit, okay, it will be from 127 to minus 128 in a signed number. Okay, so obviously minus 255 will require more than 8 bits. So this entire thing is required to represent a minus. So in that case, the carry and overflow has been set. Okay, that means this entire thing is required. This entire thing is result. If it is not set, that means okay, this much is the information. Okay, only this much also has got the total information. This is the redundant information. Okay, whereas if carry and overflow has been set, that means this is not redundant information. Okay, this entire thing together is the actual answer. Okay, so that is it is not a sign extension. Okay, that means that, right? So you got to be so you can use this carry and overflow flag to determine whether the information is 8-bit or an 16-bit. Okay, so that is with integer multiplication, right? So division is also very similar. We can have signed and unsigned. Okay, like in the case of multiplication. Now if you see the algorithms, like the Booth algorithm, if you have studied, both are different. Okay, for signed a different algorithm and an unsigned a different algorithm. So it is necessary that we tell the microprocessor what algorithm it has to use or what hardware it has to use. Okay, that depends on if your numbers are unsigned, you need to tell it is it is just okay. You can use this universally. Okay, but it will unnecessarily take here also, right? If you can use this as a universal thing, because it will cater for both signed and unsigned, but that will consume more time for implementation. For execution, this also you could use, right? But it will take. But if you are very sure you are only handling signed, then you might use this to speed up the process. Okay. Otherwise, if you are using signed, there is no option but to use this. This is slightly more complex algorithm, more hardware, and it's going to take more time. Okay. Now, obviously, now if I have to do an 8-bit multiplication, like in the case of multiplication, I just a source I don't have to declare, or I don't have to declare the dividend. Only the divisor needs to be declared. Now the dividend is by default taken as AX register. So you need to store the dividend before you give this div command. You need to store the dividend into the AX register, and you do the divisor. Now when you divide, you can get quotient and you can get a remainder also. So right, so it is not that it's going to give in decimals, things like that. So it will give the quotient. It will put the quotient into AL register and the remainder into AH register. Okay, so this has to be right. So it is generally in mathematics general, we write a quotient and then you write the remainder. So but here remainder is in AH register and quotient is in the AL register. Okay, again the flags are all we should not take into consideration the flags. Okay, so they may not be very correct. Okay, zero flag and sign flag and those things should not be taken into consideration. Okay, now if you see, if you take an example, if I have to divide 251 by 12. Okay, now this is an 8-bit information, right? So I can put it into a AL register, right? But if I do that, there could be some data which is available in the AH register earlier, right? And that can cause and when I do the division, if I don't set this to 0, it could result into a problem, right? This is just 8-bit information. So what I need to do is in the AX register 00 and FB stands for 251, so 251, right? So that I ensure that this entire AX contains the required data. Okay, so don't make a mistake of assuming this is an 8-bit data. I can just push it into AL and I leave AH as it is. Okay, so AH can have any data, right, from some previous operation which has happened. So you have to put 00 there also if it is an 8-bit data. So that is AX, okay. And then in the CL register, here for example, I have put this in 12, and then here I don't have to specify AX, okay, division. So when I do this, okay, 251 divided by 12, 20 times will be 240, so that 20 will come in the quotient, okay, that is hexadecimal 14 will come AL, and 240 and that 11 remainder will come into the AH register, which 11 stands for B, right, so 0B. So this is how this can be done. And we can also have an 16-bit divisor. So if you are declaring this as an 16-bit of the microprocessor, by default will take this data from DX and AX and do the division, and in that case, okay, this both will be 16 bits, okay, right, isn't it? So the quotient will come in AX and the remainder will go into DX. Now for example, if I have to divide 5147 by 300, right, so obviously this is 5147 and this can be accommodated in AX register, but DX, okay, that needs to be put to 0, right? So I am putting 0 in DX register out here, right? So suppose it is an 1 2 12 1 2 5 1 4 7. If it's a big number, then this 12 needs to be put into DX. In this case it is 0 0, so I need to put 0 0 into DX, and 5 1 4 7, this is hexadecimal, I am moving it to AX, and this 300 is now an 16-bit data, so I am putting it into a CX register, and then I just write div CX. Okay, now the quotient will come in AX, and the remainder will go into DX. Similarly, for a double word, you can specify in 80386 a 32-bit source also, and by default this will be taken for division. So before that we need to preload the dividend into these two registers, and the quotient and the remainder will be available in EAX and EDX. So this is how that division happens, right? After that, we'll just see talk about little bit about binary coded decimal and what is the binary coded decimal adjustment. So before that, let's understand what is binary coded decimal, right? Human beings, we deal with decimal numbers, right? So we give inputs through our keyboards or generally in a BCD format, okay, for a calculator for example, right, we give it in the BCD format. The computer does the computation in binary, and finally the output should be visible in this form, right, in the decimal form. Binary form we can't, the brain cannot grasp binary, right? If somebody instead of 8 you write it like this, right? So I will read it as 1000 like a normal human being, right? And so I need to displace this. So when this there are many applications in which the binary number, okay, needs to be converted into decimal number, okay. So a binary number, like for example, so what to do? Let's see that. Suppose I am doing an addition of 4 plus 5, right? So 4 plus 5 is 9. And this information I am suppose I am giving it to right, one 7-segment display, so 9 will be displayed, no problem. Suppose I do 8 plus 4, right? So if I do 8 plus 4, I'll get an answer of 12. So this 12 I can't give to a single 7-segment display, right? So this 12, so I need two 7-segment displays, okay, in which I give 1 here and 2 here, and then only the human eye can read it as 12, okay. So in that case, what is to be done? So obviously this is all that you need to do is you need to add another 6 to it, okay. If you add another 6, that is 0 1 1 0, right, this will become 0, or this will become 1. 1 plus 1 is 0, it will go 1 here, 0 1, so I'll get this answer. So after doing the binary addition, if I have if the answer is, okay, more than 9, okay, if the answer is more than 9, 10 or greater than, because 4-bit data can have 10, 11, 12, 13 and 15, right? So if it is 10, 11, 12, 13, 15, in that case, what I need to do is I need to add another 6, and that will become as an 2 8-bit information. So these two can drive and 7-segment displays. Okay, so I need to add another 6 to it. Okay, to convert it into BCD format. There could be another case out here. I am doing 9 plus 9. So 9 plus 9 is 18, right? So this is now, if you see this number also, if I give it to two different LCDs, right? This gets displayed as 2. And this gets displayed as 1, right? But it is 18 actually, right? Now in that case also I need to add 6. Okay, if I add 6, I will get this. I will get 18 as a display. So there are two conditions. One, if the result is more than 9, or the second condition is if there is a carry. When I am adding this, if there is a carry, in both the cases I need to add additional 6 to convert it into the BCD. So rather than writing a long program like this to convert the binary into BCD, okay, so the 8086 gives an decimal adjust after addition. Okay, it's an right. So if you see here, that will result into an BCD. Okay, so decimal, you can write this DAA. Okay, decimal adjustment after addition. So this can follow an add syntax or an add with carry syntax. Okay, either of them, and then after that, what it does, it will give the answer in the BCD format. Okay, let's take an example here. I move into AX 01, right, and I add 9 into AL, right. So what would happen? Normally if I do this, the answer is 10, right. So 10 can be accommodated in only in the AL register itself, right. 8 plus 0 plus 2 plus 0. So this is 10, binary 10, right. So I am in AX and I have 1 initially, and in AL I have 9, and I am adding right, AL and adding this to 9, right. So it is what is it doing? It is creating an problem out here. Okay, this, but I guess this is redundant. No, sorry. So this should be, let me. Okay, this is AL. Okay, see. Right, so I am moving 1 into AL, and then I am adding 9 to it, so 10. So 10 is like in AL itself, 10 can be accommodated, but that is not what is required for me, right. I have to see 1 and 0. So if I do decimal after adjust, and then it becomes like this. Okay, in AX I am going to get 1, and in AL I am going to get 0. Okay, so this helps me. So this can drive one 7-segment, and this can drive the second 7-segment. So this is how we can do the adjust, right. And in this case, this auxiliary flag, carry flag, parity flag, and 0 flag are affected, and an overflow flag is undefined. Okay, so that is, so you should not worry about the overflow flag, right. This really doesn't mean an overflow has happened. It is only that it is being there is no overflow actually. It is that this data present is now decimally adjusted into 2 registers. Okay, so that's the reason you should not it is undefined. Okay, it doesn't mean it is right. There is an actual overflow which has happened, right. Same thing, and after subtraction also there may be requirement of doing a decimal adjust. So this is what, so you can see decimal adjust after a subtraction, that can follow a sub or sub with borrow. Okay, so this can do, the decimal adjustment for sub, right. Now when I'm putting in I'm taking inputs from a keyboard, right, devices like this. So not only I am able to put figures from 0 to 9, but also I can send I can give input alphabets, both capital as well as small, and also certain symbols like space, arrows, commas, and things like that. So, and hence we have something known as ASCII codes, right? So, if you see here, all the numericals are 0, 0, 0, 0. It starts from here up to 9. Okay, and there now obviously there are so many data available, they cannot, so we require 8-bit information, okay, to cover all of them. So 8 bits are required, and not all 256 are not there, but no, it is obviously more than 2 to the power of 416, and hence you require an 8-bit in. Now if you see here, for all the this, right, for the numericals, it is 0, 1, 2, 3, 4. It goes up to, right, up to 9 out here, right. They are prefixed by 3 here. Okay, so all of them will have a unique code, and for all the capitals, if you see here, it is 0, 1, 0, 0, or if you see here, 0, 1, 0, 1. Okay, these are the two which have been used for capital. For the small, it is 0, 1, 1 zeros, or 0, 1, 1 zeros, and for the other symbols, it is 0, 0, 1, 0, right? So this is how these are the binary equivalent for all these things, right? So when you are doing arithmetic operations, and finally you want to send it for display, right? You say our computer monitor, in the computer monitor also all these can be displayed, right? So finally the binary information what is there needs to be converted to ASCII character for display on a monitor. So we have these commands, right? Adjust, then ASCII after addition, adjust ASCII after division. We have that is adjust ASCII. Okay, this is before division, and this is adjust ASCII after multiplication, adjust ASCII after subtraction. So these are the commands which are available. They also work similar to like what we did in the decimal adjust. Like for example, in the AL register, you have this data, right? 1. In the BL register, and this is what we have for 9, right? 9 plus 1. So if I add A plus 9 normally, okay, I'll if I try to add these things, I'll get 6AH, right? So what happens? This 3 plus 3 also gets added up, right? That is an 6. That is an redundant information, which is incorrect. So right. So what I want here will be, right, this, right? So I can write after the addition, I can write ASCII after add. So that will remove. What that does is that will give the answer in BCD format. Okay, that will give it in BCD format, not right. So this is in the BCD format. It will, although this is known as ASCII after adjustment. Okay, what it does is it removes these this is known as binded information along with the this is an ASCII code actually. So this 3 it removes these 3. So it removes that 6, and then it does a BCD adjustment. Okay, right? So you have this 6A, right? A indicates 10. Where did this 6A come from? 9 plus 1 is 10. Okay, that is A. This 3 plus 3 is 6. Okay, so what A does is it removes this 6 and it puts A into as 10, 10. Okay, it does in AH register, it puts this, and now from here, if I have to again make it into pure ASCII format for display, I need to write add 3030. So obviously here I will get back that 3. I will get back this 3 here, right? So what AA does is, although you might want to believe that it will do full ASCII adjustment, it doesn't do. Okay, what it does is it removes this prefix which is available from the ASCII, that this 3 it removes, and it does a BCD addition. Okay, BCD adjustment. but later on you need to add this 3030. Okay, why that 3030? Because if you see, for all the numbers this 3 is there, right? So that 3 needs to be added. No, with here and with here, right? So that adjustment is done here. Additional command is required here. So that is how it is done. Now these are it updates these flags. Okay, so 0 flag is undefined and things. So similarly for multiplication also the same thing, it works, right? So if you multiply, and if you if you multiply two things and then you do right, and adjust after multiplication, so it gets into an BCD format, right? Now 9 into 5 is 45, right? And if this is AL and this is BL, this is right, this is 9 and this is this is unpacked, right? So if you multiply these two things, okay, so 9 and 5, you will you will get this answer, right? But this doesn't make any sense. So if I do this, it doesn't decimal adjust, right? And then after that you need to add 3030 to make it ASIC. Okay, in the division case it's slightly different. We do that before the division itself, because that if that 3030 if that prefix is not removed, it is difficult in the adjustment later on. So we generally do, right, ASIC before division. It is like if this is the number which is taken, so we do the division, right? It converts a BCD to binary before the division. So if you have a BCD number, okay, which you are picking up from your keyboard or something, or ASIC number, so we need to do the adjustment as to get it into the binary format before we do the division, and hence that and then the things follow. So that is the thing. We for division, remember, division is done, ASIC adjustment is done before division. Okay, and then we give that divide command. So these are, so this is just an example. These are, I'll share the PDF here, right? So these are some of the examples you could go through, so you can see the associated lecture. Okay, so you can just go through this example also, how this. With this we will stop it out here, and in the next class we will see logical operations. Okay, thanks a lot.